Okay, so it's 2:02 now. I think we can get started. So hello, welcome to ASIC's seminar series. I'm John, the seminar coordinator, and I will be the moderator together with Kelly Medley, who is our communication specialist, and our associate director, Ralph Ferrero, also join us, and he will be introducing the speaker. Just so you know that the seminar is being recorded and it will be later published on our YouTube channel. And please feel free to ask any questions in the Q&A session. You can do so by unmuting yourself or chatting your questions. So before we get started, let our associate director, Ralph, to introduce the speaker. So Ralph, please go ahead.
Yeah, thanks, John. Yeah, I'm pleased to introduce our speaker, Professor Elizabeth Maroon from Department of Atmospheric and Oceanic Sciences at the University of Wisconsin. Let's see, Elizabeth got her PhD at the University of Washington, correct?
Other UW.
Yeah, and specializes in looking at the relationships between, looks like mostly ocean temperatures and currents with climate and climate predictability. And she's going to tell us something about the 2015 subpolar cold blob, whether that was predictable or not. And I'm sure some other good information as well. So I'm just going to turn it over to Elizabeth, and welcome.
Well, thank you all for the invitation to give a seminar. It's really nice to be able to talk with you all from Madison, Wisconsin. Give me 1 sec as I pull my slides up. Okay, you should be able to see my screen.
Yes, we can.
Great. I can't see you anymore, so if there's any questions in the chat, just interrupt me and let me know. So this is, as you can see, there's a lot of folks who have contributed to this talk. So this is was part of, I did my postdoc at CU Boulder with Chris Karnauskas, who was hanging out in the crowd there. And after that, I moved up to NCAR, where I was working on an NSF contribution to this big EU project called Blue Action. And Blue Action's focus was to look at how can we understand what's going on in the North Atlantic to try to end in the Arctic, from process to predictability. So the project I was working on as part of one of the working groups was to see, hey, we've got this one event that was super unpredictable in the CSM model that's at NCAR. And we wanted to look at, do a deep dive into this one event. So it's sort of like a forensic approach to what went wrong, and then try to compare to what happened to all of our EU partners in their prediction systems, see if they did any better. So this talk is what came out of that right before I came out to Wisconsin. So most of it will be on what's going wrong in CSM. And at the end, I've got contributions from all of these other decadal prediction systems from the EU. So where we're going to be heading this hour, I'm going to talk about how the CSM prediction missed a particularly extreme event in a location where it otherwise has very high skill. So the subpolar North Atlantic, because it has all of those ocean circulation dynamics, it's like the Gulf Stream, the Atlantic Meridian overturning circulation, things that have that evolve fairly slowly, at least compared to weather, and have predictable dynamics. We know that in the CSM prediction system that it's usually a place where you have high skill. But we had this one event in 2015 that just totally missed, which was uncharacteristic of it. So I'm going to talk about that one event, the 2015 cold blob, which is actually what has become colloquially known as in the literature. More properly would be probably the 2015 subpolar North Atlantic cold anomaly. Cold blob's easier, right? And we use it really as a case study for testing what could have gone wrong in CSM. Can we make improvements? Can we test out other approaches to initializing the predictions? And then very briefly at the end, I'll talk about what happened in those other prediction systems for this case. Was this just a really difficult case and all the systems struggled with it, or are there some that did better than others? So make sure we're all kind of on the same page. It's always nice to sort of think about where can we get predictability from? And there's really, three pieces you can use to make a forecast. So you can use the climatology, you can use initial conditions in your model, and you can use the boundary conditions in your model. So this little schematic, let's just say you've got some climate variable, temperature, precipitation, whatever, and you've got time on your x-axis. You can put together a little Gaussian, assuming your climate process is Gaussian, and say, okay, well, for a first prediction, climatology ain't bad. You've got some mean in the middle, you have a high probability of occurrence and a low probability along the edges. And over time, your observations, if you calculate your climatology right, should fill out the spread with more often than not, you're nearer the middle where you have a higher probability of occurrence. And then on the, often every once in a while, you'll hit something closer to the tails. A better forecast is if you would run your model starting from initial conditions that were experienced at the beginning of the simulation. So let's say this black line is observations. If you want to make a better forecast, start your model from where you were at time 0. And then you'll have if you run it in ensemble, you'll get a probability distribution function that gradually spreads out over time, approaching climatology. But when you're closer to the beginning, that decreased spread gives you a bit more information about what might happen. So it's sort of a thought of, forecast skill isn't just the signal. You can gain some information from the ensemble spread as well. And then throwing in this complicating wrench when you're at least thinking about climate predictions on decadal or longer timescales is that we live in a non-stationary climate. Temperatures are warming. So imagine in this case, this temperature climate variable is, it's temperature. Things go up. And this trend is due to some boundary condition forcing. So for example, greenhouse gases, ozone, aerosols. So you have a climatology plus a trend. And putting all the pieces, then you can add some observations and you see in general, there's an upward trend. And if you put it all together, so you use your initial conditions, your boundary conditions, your climatology, you can this is basically the decadal prediction problem. How do you predict stuff best on a 5 to 10 year time scale with initial value predictability, so what's going on at the beginning, but also incorporating those any kind of external forcing, forced predictability from greenhouse gases, as well as other constituents in the atmosphere. So those are kind of the three ingredients that go into these kind of 5 to 10 year long data sets. And so this is a nice schematic from one of Jerry Neal's papers. You've got everything, a spread from the daily weather forecast, which is an initial condition problem, all the way out to the projections of IPCC class models, where really most of what's going on is dictated by how much greenhouse gas you have in there. So the external forcing. The decadal prediction problem has because of its time scale and the dynamics and how long things work in the ocean, you get a mix of both. So some of the initial conditions from the ocean will give you predictability. And then it's long enough that you can see predictability from anthropogenic forcing as well. So this talk actually is a little bit to the left of that decadal prediction side. So I'm going to be talking on seasonal to 1 year timescales. And the reason why is because the CESM-DPLE, particularly in the subpolar North Atlantic, it matters how your climate is evolving on that 1 year timescale for what happens later. Or a simpler way of putting that is, if you're wrong at 1 year, that is going to affect what's going on at 5 and 10 years. So you want to make sure that at the beginning of the earlier parts of your run, your prediction, that you're doing well. So the main data set I'm using is the Community Earth System Model 1 Decadal Prediction Large Ensemble. So that's a big mouthful. This followed the CSM1 Large Ensemble, so the Decadal 2015 data set, where you had basically you reran a climate projection through the historical period and then projected into the future 40 times. This followed the same exact protocol, except it did it in hindcast mode. So trying to go back and say, okay, we've got, what if we had tried to predict what had happened starting in November 1, 1954, November 1, 1955, November 1, 1956, et cetera, and run it the exact same way. So instead of, a forecast, it's a hindcast. So the way this one works is you start from some sort of initial conditions that are based on some approximation of the observations every November 1, and then run them out. Why November 1 was chosen? It's because for at least the North Atlantic, that's going to get you a little bit ahead of all of the important things that happen during the winter time in the Labrador Sea, the Irminger Sea, for convection in the North Atlantic. So each of these hindcasts, there's 64 of them, I think, from 1954 out to initialized in 2017, have 40 ensemble members, and each one's 10 years long. The initialization is probably worth noting because I'll be talking about some modifications we made to the initialization later. So in the ocean, the initial conditions are actually not pulled directly from observations, because in CESM, you need initial conditions for all sorts of fields that we don't have observations for. And even if you go back a little bit further prior to the satellite era and prior to Argo especially, I'm not sure we trust what observations we have well enough. So the approach that's used at NCAR is instead to create what they call a FOSI simulation, forced ocean sea ice. And so you take the atmosphere reanalysis. In this case, it was an adjusted NCEP NCAR reanalysis, and you drive an ocean and sea ice only model from the CESM framework with the reanalysis. And by driving it, you're constraining the oceans and sea ices to what happened in the atmosphere. It's not going to be a perfect representation of what occurred in the ocean, but it'll give you all the fields you want to initialize. So not just temperature and salinity and ocean velocity, but all of the biogeochemical fields as well. So you can, one of the neat things, I think this was the first prediction system on this kind of timescale that has Earth system predictions. So not just physical fields, but also ecosystem relevant fields like dissolved oxygen, all sorts of carbon pools and all sorts of things like that. So that's this full field initialization approach using this FOSI simulation is something that makes this prediction system a bit different from other ones. So that's where you get the initial conditions from the ocean and the ice. This will become important later. In the atmosphere and land, it was a different approach. So because Decadal timescales really make you think, okay, it's got to be ocean dynamics that's giving you that. And it really doesn't matter what's going on at the very beginning with the atmospheric weather. This data set used one of the restart files from the CESM-1 large ensemble for its atmospheric and land initial conditions. So the initial conditions in the atmosphere and land have no resemblance to observations whatsoever. And the idea is, once you're further out than a month, it doesn't matter anyway. It's all going to be down to those more slowly evolving components of the Earth system. So that's the data set we're using. And it's actually quite skillful in many places. This is an SST anomaly correlation coefficient. So in red, where it's 1, that's a perfect forecast. Blue is the opposite of what you expected. So, your anomalies, you hope that your anomalies in the prediction system, the observations go together. And then white says there's no correlation whatsoever. So you notice that there's some places, even out, to 5 to 9 years after initialization, where you have really high, going up to 0.9 correlation between observations and the hindcast. You'll notice there's some places that don't do really well. Lots of stuff going on in the Southern Ocean that's just wrong, as well as it looks like there's room for improvement in the Eastern and tropical Pacific as well. So it's always good to say, okay, well, this is our forecast. How does it do against other possible forecasts? So one low bar is a persistence forecast. So the idea that you take, if you're doing a forecast today, what happened yesterday is your forecast. So if you take all of the yesterdays and you calculate the improvement in the anomaly correlation coefficient in the DPLE over a persistent forecast, that's what's in this middle line here. And you can see that there are some locations, anywhere it's red is an improvement over a persistent forecast. One place that kind of jumps out, especially 5 to 9 years in the future, is the subpolar North Atlantic. You have a lot more improvement in anomaly correlation coefficient over persistence in the North Atlantic. An even higher bar to exceed is the bar from the CSM Large Ensemble, which is effectively, these two large ensembles are identical except for the initialization. They have the same forcing, they're the same resolution, same model mechanics. So if you're using the large ensemble as a forecast, or sorry, a hindcast, and you take the difference in their anomaly correlation coefficient, that'll tell you where you're getting skill from the initial values, the initial conditions. And the one place that really stands out is the subpolar North Atlantic. So that's this red area, even out 5 to 9 years. And that actually is, there's been a ton of work over the last 40, 50 years that tries to connect the dynamics in the subpolar ocean to connections in climate far beyond. So this would be, this kind of subpolar North Atlantic SST is connected to things like the Atlantic multi-decadal oscillation or Atlantic multi-decadal variability. And there's a lot of, so for example, that has ties to the amount of Sahel precipitation, hydroclimate in the Southeast US, European temperatures and droughts, the monsoons in India. I think there's a weak correlation with stuff going on there and into Asia as well. So the fact that we have predictability in this one part of the ocean is suggestive that we have the ability to improve predictability in all of these other important climate impact places. So here's the problem that I've had. So the CSM-1 Decadal Prediction Large Ensemble, it really does a good job capturing the low frequency variability in all the forecasts. So here in black, this is the SST in the subpolar North Atlantic from your SST. Orange is the DPLE, the spread is the shading, and then the ensemble mean is in the darker orange line. We have year 1 predictions, year 3 predictions, year 5 predictions. So trying to see how each of these different lead times do. And for the most part, the observations fall within the range of ensemble numbers pretty darn well, except in 2015. So that's where I've got this little arrow pointed at. And you can see that this basically, it gets worse as you get further into the hindcasts, further into the evolution. So by the time you're at a year 5 prediction, the ensemble is saying you should be warmer than normal. And the observations are colder than normally. So you can see that while most of the time subpolar North Atlantic's doing well, this one event was just a total whiff, totally failed. And so that's what we're trying to understand is, what went wrong here? Can we learn something about how the system works and how we can improve our the prediction framework for the next version? So now I'm going to take a bit of a break and shift and talk about what this event actually was, because it was actually quite extreme. So this is the event that is now known as the 2015 Subpolar North Atlantic Cold Blob. So we've got cold blobs, and then if you're up on the marine heat wave literature, there's other blobs over there too. This was almost record-breaking, depending on where you're at. There were a couple of pixels and observations that broke records. In terms of the whole subpolar North Atlantic average, it was pretty darn close to near record. Something that made it particularly unique is just how large it is. So it peaked in summer 2015 and covered, spanned most of the North Atlantic. That's pretty remarkable in terms of the size of the anomaly. So in addition to wanting to understand why the system broke, this event also has some pretty big societal relevance. So there's been a couple of studies, particularly there's one from Jennifer Mecking in 2019, that shows that SST anomaly contributed to the 2015 European heat wave that occurred at the same time, that you wouldn't have had nearly as severe a heat wave without the cold blob there. So this is just, this was an important event to try to get right because you had these extreme events that were tied to each other. More of relevance to what I'm working on is using this as an event to try to test new decadal prediction protocols and setups, and using it as an opportunity to understand what went wrong, how sensitive are we to different types of initial conditions. And we also used it to test a new to CSM initialization procedure that doesn't use that forced ocean sea ice simulation. So let's talk about what happened during this event. This event actually started in fall 2013, but the predictions failed starting, even if you start from a cold state in November 2014. So I'm going to be focusing only on those shortest lead time forecasts for the event. So starting in fall of 2014. But so by fall of 2014, you've got this is SST up here on the top in the fall. And you can see you already have a cold blob there, even at that point. It amplifies as you get through winter, spring, and then summer. And particularly in summer, you can see that it's much larger. It's also important to note that this wasn't just an SST event. This was really a whole upper ocean. This anomaly stretched down to about 1,000 meters depth. It wasn't just a surface event. So as an indication of that, I've got the 300-meter average temperature from EN4 at the same time periods. So you can see this cold blob really peaking at an upper ocean temperature, sort of in the same spot as where you can see the peaks in SST, but not quite the same. And you can see it's much more stationary and it doesn't grow as much as what was going on at the surface. So it's sort of more stable in space and magnitude. So for the SST, since that's kind of what went particularly wrong, if we look at observations, there were 2 periods of cooling that occurred after 2014 that if you wanted to get to prediction, you needed to capture these. So the first was from January to April. You had a drop of about 0.2 degrees Celsius. And so that doesn't sound like much, but it was really important probably for sustaining this event. So during that spring, you had a very positive North Atlantic oscillation. And when you have a very positive North Atlantic oscillation, you basically have stronger westerlies, you can get way more turbulent cooling. And because in the wintertime you have deeper mixed layer depths, you're able, that cooling is not going to be a huge amount in any one spot, except in terms of the heating. So you're basically, this is sustaining the cold temperatures throughout the entire mixed layer. So you only get a slight intensification. You can contrast that with what happened in May through July, when you had a decrease of 0.6 degrees Celsius, which was quite the drop. That's very unusual. And it turns out because in the late spring and summer, you have very shallow mixed layers, it doesn't take much of a cooling to really decrease things pretty fast. So, you know, if you look at reanalysis, it was only a cooling of roughly 10 watts per meter squared that gave you that decrease of 0.6 degrees Celsius that really amplified the cold blob. So one of these pieces, you know, might be predictable. You know, there's some indications that some systems are able to predict NAO months in advance, some aren't. But I would argue that 8 to 9 months in advance, you're not going to be able to predict exactly a 10 watt per meter squared surface heat flux. That's kind of on the small side. So this is just a quick plot of surface heat flux anomalies from the ERA interim and had SLP2R. So shading is net heat flux anomalies. Red is warming the ocean, blue is cooling the ocean. And then contours are the sea level pressure anomalies. And all I want to point out is the intense cooling you have where you have those strong sea level pressure gradients in December, January, and especially March. And that's the indication of a positive North Atlantic oscillation that really drove you that cooling and sustained the event. So I'm going to argue that there are 3 features that you needed to get right to be able to include a cold blob prediction in your ensemble mean. You need a reasonable initialization, and at both the surface and in the upper ocean. So this wasn't just a surface event. You could think that, you know, if you don't have that cold anomaly at depth, you're not going to be able to really sustain it throughout the winter as well. You might also say that, well, you want a positive winter and spring North Atlantic oscillation prediction. Well, that's a bit tougher. Some prediction systems on these multi-year timescales, and I'm thinking in particular the Depressa system, are able to predict NAO out months to even, you know, a year 2 prediction with skill. CSM can't do that, but others can. So, you know, this is one of the things, maybe this isn't possible to do for this event, but it is a feature that you would need if you wanted to get this event well. And then out towards the summertime in May through July, you'd hope you have sufficient spread in the range of surface heat fluxes, just to give you possibility that you are able to have a couple of ensemble members that have surface amplified cooling. And then I've got a fourth kind of thing that you need. Well, you need a model that represents North Atlantic climate process well enough. If your model really sucks at everything going on up there, you shouldn't expect it to do well in the first place. So let's look at the predictions themselves. So this is the month one prediction as a sort of, grounding of, are we doing well at the beginning? So on the left upper top here, that's SST anomaly and ER SST. The bottom left is the month one prediction if you had taken that FOSI simulation. So this is the one that's constrained by atmospheric reanalyses. You would say, well, if this is what's giving us our initial conditions for the ocean and it's totally out to lunch and it's not got a cold blob, well, you wouldn't expect anything initialized from it to have a cold blob either. But it does reasonably well. And then we have the ensemble mean from the prediction system in November 2014 up in the right corner with an indication in the bar chart showing a histogram, of the number of ensemble members where they lie in terms of their SSTs. And then the black line indicates the observed SST anomaly, and the red line is the SST anomaly from the forest ocean sea ice simulation. Maybe the DPLE is a little too cold, maybe, but it does have a cold blob. So we started from a place that looked right. And this is what happens by June, July, August of 2015. Observations have a big cold blob. The FOSI has a very large area of negative anomalies. But the ensemble mean for our prediction system is positive. You can see this in the spread of the ensemble members. There's only 3 ensemble members that even have any kind of cold anomaly, much too weak, whereas the observations are indicated down here by the vertical lines. So the DPLE, and this is going to be a common theme, really likes to warm up in this case for some reason. Here's another way of viewing that. This is a time series of the SST anomaly. Solid line is ER SST. The dashed line is the forest ocean sea ice simulation. And the gray shading in line is the DPLE itself. And so you can see that the observation and the FOSI fall within the range of ensemble members up until about May of 2015, right before you had that little bit of extra cooling due to just surface heat fluxes. But one thing that's really remarkable is that even from the beginning, the ensemble mean shows this upward trend. And so that seems to be something that's particularly problematic with what's going on, is it just wants to warm up no matter what you do and not stop at climatology at 0. It wants to overshoot into a warm anomaly land. The upper ocean heat content anomaly, so this is the upper 300 meters, is also not particularly well. In this case, there's a discrepancy between our observation observation-based metrics, so EN4, which is more closely related to direct observations, and our FOSI, which is kind of, you can use it as a stand-in for truth. So the low bar is if the FOSI is encompassed by the spread in the DPLE. The higher bar is if you capture EN4. And while FOSI is at the very, very lower edge of the range, it is at the very lower edge of the range. The ensemble mean warms up even in this upper ocean a bit more. So that's also not the best forecast. So we can take a process-oriented view of what went wrong, what is going on differently in our forest ocean sea ice simulation compared to the DPLE. Because as a climate model simulation, we have access to all of the budget terms and can really diagnose what happened. So that's what we've got here. We've got a heat budget from the FOSI simulation, which we're going to use as a stand-in for truth. So black line is the total heat tendency. Blue line is the ocean advection, so ocean currents that are resolved. Orange line is the net surface heat flux, and green is the combination of all of the subgrid scale processes. So green, blue, and orange add up to black. When it's positive, that indicates you've got ocean heating. When it's negative, that indicates ocean cooling. And so you can see there's particularly in the FOSI, 2 periods where you had a lot of cooling tendency. And that's in January and March, when you had those very strong positive NAO conditions. And this makes sense that both surface heat flux and resolved ocean advection should have an atmospherically driven component. So this blue line isn't like the very, most of that's not the slow ocean response. Most of that's Ekman, so wind driven. So we can take then those two processes, so surface heat flux cooling and the resolved advection, and compare them against all of the ensemble members in the DPLE. And what you'll see is that in those 2 months especially, January and March, the FOSI falls well outside the range of all 40 ensemble members. In general, the ensemble mean is the opposite sign of what occurred, and there's no ensemble members that are as negative, that have as much cooling due to those two processes. So this suggests that it really is, the DPLE is missing the atmospheric forcing that is key for sustaining the event. So we can, my computer, there we go. Computer's starting to take off here for some reason. So the CESM-DPLE, we can look at this directly. It does not capture as positive of North Atlantic oscillation conditions as occurred during 2015. So here we have time series. Ignore the color for gray and purple for now, and black is the observed NAO strength. And if you do this month by month, you can see that maybe there's one ensemble member that captures stuff as positive going on as was in observations. But what's really remarkable is if you take a 3-month running mean, none of the ensemble members have as a sustained positive NAO conditions as occurred. So none of them are able to get multiple months of very positive, very strong westerlies. So this leads us to possible hypotheses for, okay, why was this connection why was the observed atmospheric circulation and the observed cold blob not produced by any ensemble members? One possibility is that CSM just cannot produce this magnitude of extreme cold event, even in its pre-industrial control, even in its, the CSM1 large ensemble. Another possibility is that this is just a super rare event, like a once in the historic record kind of event. Maybe we could add more ensemble members, but maybe it's just not predictable. And then the third possibility is that there's something about the initial conditions that's just inadequate. There's something wrong with something that can be improved. So in the interest of time, I will just tell you really quickly that CSM1 can predict cold events at least as cold as the 2015's cold blob. So in CSM1 large ensemble, 1 out of every 50 winters has a cold event just as cold. And it turns out that agrees pretty well with the frequency you can find, frequency of cold events in reanalyses. What's more remarkable is that the CSM1 large ensemble really doesn't produce many DJFM NAOs that were as positive as was observed. That's a 1 out of that. If you believe the large ensemble, that was a 1 out of every 440 winter event. And based on the ensemble range you can get from the large ensemble and the longest observations we have, we think that those are at least consistent. We can't distinguish them any differently. So in terms of, well, if the NAO is not important, maybe we could add a few more ensemble members and try to get up to that 1 out of every 50 threshold to see if we get a cold blob. But it's this, the rareness of this NAO event in the CSM, and possibly in the real world also, is that it's unlikely that you're going to get an NAO event of this positive magnitude predicted purely by chance, if you assume that the NAO has no initial value predictability. So the first thing we tested was, let's do the easiest thing and just expand our ensemble. We added 20 more ensemble members, and what we found is that there was no improvement in subpolar SST or the NAO range. So here's a histogram of summer SST. The blue are the original 40 ensemble members, and the orange are the new ones. And you can see that there's no improvement. The SST is still warming up, and that it hasn't increased the range in any way. The purple on this side is the additional ensemble members. That also hasn't, you haven't gotten a more positive NAO event by adding a couple more. and that's probably expected. So, maybe one possibility is that this event, because of how extreme it was, is just not, there wasn't much initial value predictability, so it's not really well predicted. That's possible. The other possibility, and maybe what we're going next, is that something about the initial conditions is inadequate. And I'm going to tell you now that that's likely. So after studying this event and what the DPLE looked like, we found 3 initial condition related deficiencies that could have had an impact either on the SSTs in the upper ocean themselves or on a subsequent evolution of the atmospheric circulation, so on the NAO. The first one is that this one hindcast in the CESM-DPLE had way too much Barents-Kara sea ice, which some studies have shown is connected to later atmospheric circulation in the region. So the hypothesis there is that, well, if you've got too much Barents-Kara sea ice, you're messing up the NAO evolution. So in the interest of time, I'll just tell you that we ran a sensitivity experiment where we improved the evolution of Barents-Kara sea ice, and we made the prediction worse. So that's a nice way of crossing that one out. So even improving that feature didn't help. The next thing I will tell you a bit more about. So the subpolar North Atlantic's upper ocean is too warm and too fresh. So here I've got temperature anomaly over time. So November is on the left, 2014 on the left, 2015 on the right. I've got EN4, so an observation-based metric on the top, and then the FOSI simulation below. And you can see, so temperature on the left, salinity on the right, depth on the y-axis. And you can see that the FOSI is way too shallow in terms of temperature. So that there's the cold blob in the FOSI, very, very surface close, and it doesn't have nearly the depth of the observed event. But perhaps even more disconcerting is that it has the wrong sign of salinity anomaly. So there's this cold blob turns out is also a fresh blob. And the FOSI does not want to do that. So the DPLE inherits these issues from the FOSI. It doesn't have a very deep anomaly. And you can see that the very beginning, especially the temperature anomalies and the salinity anomalies very much follow what happened in the FOSI. And then once the atmosphere is let go, you can see that you're able to, there's that too much warming that evolved. And it could be because of the stratification and the upper ocean conditions just aren't correct. So what we did was we tested an anomaly initialization approach for the first time in CESM. So this differs from the approach using the FOSI. So use the FOSI as your initial conditions. Instead, this time, we're going to do a different experiment. So for our control, we have taken the CESM-1 large ensembles climatology from November 1 and used that to initialize a first experiment where you just want to know, okay, if it's 2014, but we use a climatological initial condition, that should give us the, what a normal forecast, normal response would be. And then our anomaly approach is then we take EN4 and take its anomalies in temperature and salinity and add those to CESM-1 large ensembles climatology. So we're adding anomalies on and we initialize from those anomalies. And the idea is that the difference of these two experiments should show us the, hopefully kind of in a different way, what the impact of those initial conditions are. So this was the first time we tested out this kind of approach in CESM-1. It's something we're still, I'm still collaborating with folks at NCAR who are thinking about this and using that. So there's a postdoc there now, Shan Wu. She's working on, she's got some interesting, she's using this approach also to test the, the impact of volcanic forcing in these kind of predictions. So we used EN4 anomalies to initialize, and here's our, we actually got quite a bit of different structure in our temperature and salinity anomalies. Perhaps most encouragingly, we actually have a fresh blob now. We still don't seem to be able to hold on to a cold anomaly in this CESM hindcast, but at least we're not warming up anymore. So this is a minor improvement that maybe we've, maybe if this event weren't predictable, that at least now we are near the ensemble mean. So in terms of upper ocean heating, this is still an issue. Then the last sensitivity experiment I'll tell you about gets back to what I mentioned at the beginning of the talk about the DPLE's atmospheric initial conditions. These are not based on observations because the presumption is that on longer timescales, which is what the DPLE was made for, it doesn't matter what the weather was at the beginning. But it might matter for this case, how things are set up in the first month for what happens a couple of seasons down the road and 1 year down the road. So we took ERA interim reanalysis, and instead of using the CESM-1 large ensemble for initial conditions, we used an observation-based initial conditions in the atmosphere. And we made a worse prediction. So this was particularly eye-opening and interesting. So these gray simulations here, that's the original hindcast. Blue is observations, and orange is this new sensitivity experiment using atmospheric initial conditions that are close to observations. And you can see that from month 1, you have a neutral or warm anomaly. You don't even have a cold blob from the beginning. So what's going wrong here is actually that the CESM-1 DPLE has an initial dip in temperatures during the first 2 weeks. And you can attribute that dip in temperatures to the CESM-1 large ensemble atmospheric restart file that was used as initial conditions. The CESM-1 large ensemble does this exact same dip in the first 2 weeks. In effect, because of the atmospheric conditions, you were getting the right answer, but for the wrong reason. And using a better approach, so something that's based on what was observed, actually made it worse. So this was pretty confusing, but it's helpful to know. So the next version of the CESM-1 DPLE, there's a new version now using CESM-2. It does now use a reanalysis for its atmospheric initial conditions. But this was particularly interesting to see. So briefly, in the last couple of minutes, I'll just mention, what about all those other prediction systems that have hindcast available for this event? I'll show you just some brief results from those. They have all sorts of different resolutions. Most of them have November 1, October, or January 1 type of start dates. They all use very different initialization techniques. Some of them use full field techniques like CSM. Some use data simulations, some have anomaly initialization, some use nudging, some have pretty sophisticated DA approaches, all over the place. So, no hindcast ensemble mean. So that's these solid lines here. This is again SST anomaly. Really, we're able to capture the depth of the cold blob, its intensity. But there are some ensemble members that did, particularly from the Depressis system from the UK Met Office. So that's these light blue lines. Those are a couple of ensemble members. And the Norwegian hindcast that I have, so in orange, green, and blue, also have some ensemble members to get closer. Those are smaller ensembles, only 5 to 10 ensemble members. So you can imagine if you had 40, like CSM or Depressis system, maybe some of them would have captured that. And then up on the top is all of the additional CSM simulations since I started working on this that have come out. So the new CSM-2 prediction data set, SMILE. And you can see that even in SMILE, the CSM just really wants to warm up from this event. So there's something very peculiar going on in CSM in there. And then this is just a spatial look at what's going on. This is month 1. So the contours are HAT-I-SST, so observations plus or minus 0.5. The colors are the anomalies in each hindcast system. So you're trying, and they start at plus or minus 0.5 degrees Celsius. So you're trying to match the contour with the first color as an indication of, did they get the approximate location right during month 1? And the answer is, for the most part, yes. There are a couple like EC Earth and the IPSL hindcasts that are a little bit out to lunch, but most of them, the CSM suite, Depressis, Norwegian, are all pretty much the same place. But in terms of ensemble mean, which is in the summer of 2015, There's some that still have cold anomalies left in the right place, but none of them really match the extent or intensity of what was observed. So we go back to that initial set of things that happened. You can use all of these ensemble members as one big multi-model prediction. All right. So we've got 100 odd ensemble, more than 100 ensemble members. If you take the full hindcast mean, you see there's a weak cold blob you get from in all of those ensemble members. And then if you subselect just for those multi-model ensemble members that have NAO that's greater than 2, you can see you get a much better representation of the cold blob. And you can see there's some indication in these coastal SST areas that you are also capturing some of the European heat wave more than you were just the ensemble mean. Same thing goes for if you're subselecting just the ensemble members that have weak surface cooling during May and June. So these are those ensemble members. You have something that actually is just about the right location, but not quite as strong. And then if you subselect for both the conditions that occurred where you had very strong NAO and negative surface heat flux, you can get a much larger area of negative SST. The pattern is kind of off, but these were the conditions that occurred. There were only 4 of the multi-model ensemble members that had this. So there's something about this event that was particularly challenging, and perhaps it's something that just wasn't predictable. The atmospheric forcing was so important in it, and for the most part, that atmospheric forcing is not predictable that many months in advance. So in summary, the 2015 subpolar cold blob, it was a near record event that impacted European climate, and it was poorly predicted by NCAR's CESM-Decadal Prediction Large Ensemble, which otherwise does fantastic in the subpolar North Atlantic. And this provides an opportunity to figure out how can we improve future CSM climate prediction systems. We found deficiencies in CESM-DPLE's initialization, but because of the really important impacts of the NAO, as well as that later surface heat flux forcing, this event may not be very well predictable because of just the limits of predictability. A few other hindcast models were able to include this cold blob in their range, but none of them really showed it in the ensemble means. So before I open up for questions, I just really quickly want to mention a couple of other things that we're up to here in Wisconsin. So I've been here starting since the pandemic, and I'm slowly building up a research group. So one project that we're working on, RA Tadra Lowe is looking at how North Atlantic ocean model biases are related to, so biases in SST and salinity are related to what's going on in the location of the Gulf Stream and North Atlantic current. So we're looking into how do SST and biases feed back later onto the rest of the thermohaline circulation across CMIP class models. And then also have a project working on marine heat wave predictability. So working on both ends of the extreme, cold blobs all the way to marine heat waves. R.A. Evan Meeker has been looking in different CSM simulations predictions, so the DPLE and now SMILE, to see where do we have multi-year predictability in marine heat waves. And he's been focusing first on the big event that occurred 2013 to 2015, the so-called the blob, so not the cold blob, so that was particularly damaging off the west coast of North America. So again, thank you very much for the invitation to speak, and I'm happy to have a discussion and answer questions as long as you all are interested.
Thank you, Elizabeth. David typed a question in the chat a couple minutes ago. David, if you want to go ahead and answer that or ask that, now's your time.
Hi, Liz. Nice talk. So I had a question about the shorter term mechanisms versus longer term mechanisms. So longer term mechanisms cause the North Atlantic warming hole. That's what I'm thinking. It's the same region. So I'm just seeing some parallel. And I mean, so people have found that the subpolar gyre contraction and AMOC slowdown and shortwave radiation getting to the surface because of low cloud changes, all those are important. How do those contrast or compare with the shorter term mechanisms you're studying?
Yeah, that's definitely relevant. So right, there's this warming hole that's coming about because of anthropogenic forcing, and you can also see it due to low frequency net variability. So if you look at, I think the magnitude of how much something like that could impact things, it's much smaller than this really rapid cooling that you get due to NAO and a positive NAO. So it's sort of the way I've been starting to think about it is there's a difference between a warming hole and a cold blob. Like these cold blob events seem to be more atmospherically forced. So if you go back to like the Hasselman model, something along those lines, that where you go back to a climatology after some initial perturbation. Whereas the warming hole or whatever else is due to low frequency variability is, as you said, all of those gyre processes, those slower things. And my feel for what's going on in this event is that it's really the weather time scale and the NAO time scale stuff that's important in the prediction. And it's the processes you mentioned that actually have the predictability in the DPLE out 5 to 10 years. But I haven't quite figured out how do you connect one to the other in terms of how these predictions, if you start out with not getting the atmospheric forcing right in this one prediction, it totally degrades the prediction later on in SST and in probably circulation fields.
Just one follow-up on that. So you have some of the same symptoms as a model that wouldn't get the warming hole correct, though, with the erroneous surface salinity. So there have been studies now that show that the amount of ocean heat uptake that you get over a long time period is related to the anomalies that you have in sea surface salinity, and it looked like, well, at least you couldn't rule it out yet. That could be one cause of the errors. So, yeah. But it's on much shorter timescales, and so I'm just trying to tease this out.
Yeah. So that issue where the salinity and the temperature are not they're not working together, that came from that forced ocean sea ice simulation where you were constrained by the atmospheric field, perhaps unphysically. So you're pulling things back to where the atmosphere wants to be observed, but maybe you're getting the ocean's evolution constrained not in the right direction. I actually had a summer intern who was looking into the CSM2 pre-industrial control to try to look into when you don't have anthropogenic forcing, what does the average cold blob look like? And so that's something she was working on last week, is filtering out, okay, if we do a high pass filter, what does a cold blob look like? And then if you subtract that, what is a lower frequency cold blob look like in terms of surface heat fluxes, salinity, and all of that. So don't have much more of an answer for you other than it's something I'm thinking about.
Thanks.
Any other questions? If you do, you can raise your hand or just unmute yourself or type it in the chat. Any of the above.
I have another question. Thank you so much. It was super interesting. I was wondering if you could explain maybe a bit more why the NAO is so correlated to the surface heat flux patterns. So when there is such a strong NAO, why the surface heat fluxes are so strong?
Sure. So two pieces. One is that, well, I guess one of my pieces is it's evaporation and sensible heating. So when you have stronger sea level pressure gradient, you have stronger westerlies, and when you have stronger westerlies, you can, if you imagine just like a bulk formula type approach to evaporation. So, your drag coefficient times the magnitude of your wind times the difference between, either temperature air and temperature salinity or specific humidity, above and below. You'll have a stronger evaporation. So that's really what it is. And then there's also the Ekman part, but that's not the net surface heat flux.
Okay, thanks.
Any other questions before we wrap up? Okay, well, unless I'm interrupted in the next couple of seconds, and please feel free to do so. I think we can close off today's seminar. Thank you so much, Elizabeth, for coming to talk to us today, and everyone else for coming. This has been a great talk. And so everyone have a wonderful week. So we will not have a seminar next Monday because I assume everyone will be at AGU or participating in AGU somehow, but we do have our final seminar of the semester, and that will be on the 19th, so week after next. So thank you everybody so much. Hope to see you again.
Thanks again for the invitation.
Yeah, thanks for talking.